Okay, so now let's take things out to the most general case that we're going to consider in section, say we're working in section 3.4 from the reading materials, where now we're going to solve a system of differential equations that looks like x prime is ax plus by, y prime is cx plus dy, where all of these constants or coefficients a, b, c, and d are constants. So we would call this a system of linear differential equations with constant coefficients. Okay, so what we've seen so far is that it makes sense that we're getting solutions of the form c1 e to the r1t, c2 e to the r2t, and y is having the same powers, but these coefficients, these arbitrary constants, might be different. And what we saw in the previous example is that there is some codependence on the arbitrary constants in one of our solutions with the arbitrary constants in the other because those two populations are interacting with each other. And what I'd like to do is figure out what are the conditions that these constants over here, that these powers R1 and R2 need to satisfy. So when we were working with second order differential equations with constant coefficients, we kind of guessed what the solutions might look like. We plugged them into the differential equation, and then we saw that as long as these values were roots of a characteristic equation, then that's going to generate solutions. So I want to develop a similar general method that we can apply to figure out what are the conditions on these values R1 and R2 in order to figure out what our solutions are. So first I want to start with this equation for x prime. And what I'm going to do is plug in our suggested form of the solutions for x and y up here and see what some of the resulting conditions are. So for example, if I were to take the derivative of x, then I would get x prime is equal to c1 r1 e to the r1t plus c2 r2 e to the r2t. Okay, just by taking the derivatives. And what I know is I would like that to equal a times x. So I'm going to take a times all of the terms in x, which was c1 e to the r1t, plus a times c2 e to the r2t. And then I'm going to add to that b times our general solution for y. So I'm going to get b times c3 e to the r1t plus b times c4 e to the r2t. And then, like we normally do, we'll group up our like terms. So let me group all of the e to the r1 terms. So there's that one, and this one over here. And so by matching up the coefficients in front of the e to the r1t, I can see that what I would need is c1 r1 would need to equal a c1 plus b c3. And similarly, by grouping up the r2 terms, I would get here that c2 r2 is going to have to equal a c2 plus b c4. So I've got a couple of conditions that I know R1 and R2 need to satisfy, and those conditions depend on the values of these coefficients, in this case a and b. And let's do a similar analysis with the solution with the differential equation for y. So if I am guessing that y looks like this, then let me use this equation for y prime to figure out some additional conditions on R1 and R2. So again, we would say, well, if y is equal to c3 er1t plus c4 er2t, then y prime we get by applying the chain rule, and we would get r1 c3 e to the r1t plus R2 C4 e to the R2 t, and all of that is going to have to equal c times x. So that would be a c1 e to the R1t plus c times c2 e to the R2t, and then we're going to add to that d times y. So I'm going to get d times c3 e to the R1t plus d times c4 e to the R2t. And then we match up our terms. So for the R1 terms, I've got this one, and I've got this one, and we've got this one over here. So altogether, we get one equation that says R1 C3 should equal C C1 plus D C3. And then taking all of the exponential terms that have a power of R2, then we would get an equation that says R2 C4 is equal to C C2 plus D C4. And so we've got four equations. Two of them, namely this one and this one, involve conditions on R1 that R1 needs to satisfy. Two of them, this one and this one, involve conditions that R2 must satisfy. So let me group those together separately. So R1, it needs to satisfy that C1 R1 is equal to A C1 plus B C3, and C3 R1 is equal to C C1 plus D C3. And the conditions for R2, these are the ones that were in blue. The first one was over here where we had C2 R2 was equal to A C2 plus B C4, and then we had that C4 R2 needed to equal C C2 plus D C4. And so in the end, we get these very kind of linear looking systems of equations. So we're going to be able to apply some results from linear algebra and use them to solve systems of differential equations. So section 3.2 in the textbook goes through a pretty in-depth review of some of the concepts of linear algebra that you would need. I'm going to go through some of them in these slides. If you've had a course in linear algebra, then you might be able to skip some of these. If you've never had a course in linear algebra, then you definitely should read over these materials pretty carefully, and I'll do some examples in the next couple of slides. So we're going to kind of take a detour in the next couple of slides into linear algebra, and then we'll connect it back to what we were looking at in this slide and how we can find the general method for solving systems of linear equations that look like this one.